Okay, so I started telling you about yet another tool for computing limits of sequences. What is this tool? Well, it's the following theorem. So if you have a sequence such that its limit is known, so maybe when n goes to infinity, the limit of an is a number, L. Finite number, this is a convergent sequence. And so if in addition to this sequence we have a function which is continuous at this very value, L, then you can compose the function with the sequence, obtaining that the limit when n goes to infinity of f of an is, and here comes the interesting part, if you have a continuous function, specifically a function continues at the limit of the sequence, you can interchange the function with the limit. Important here that the function is continuous. This trick doesn't necessarily work for non-continuous functions. And so this here is equal to the f evaluated at the limit when n goes to infinity of an's, and that is to say, because the limit is equal to L, this is equal to f of L. And so this is a way to compute limit of a sequence if you can express it as a composition of a continuous function with a convergent sequence. For example, let's compute the limit when n goes to infinity, sine of pi over n. Right? So here, proceeding with the tools that we had previously would be quite tricky. And so we don't quite have a squeeze theorem for this. Cannot apply limit laws. So what we can do here, though, is the following. You can say, well, look, sine of x is continuous. Well, it's continuous everywhere in its domain, but most importantly for us, it's continuous at 0. Why do we care about 0? Because limit of pi over n when n goes to infinity is 0. So the sequence inside is a convergent sequence. Specifically, it goes to 0. And so by the theorem, we conclude that limit when n goes to infinity, sine of pi over n, and it is important here that the function is continuous. So if it is the case, then this limit is equal to the sine evaluated at the limit when n goes to infinity, pi over n, and so that would be sine of 0, which is also 0. So it is important that the function that is being composed is continuous, and if that is the case, you can interchange the limit with the function. So the moral of this is limits can be interchanged with continuous functions. Okay, as a final example for squeeze theorem, I want us to look at example 10, which considers the sequence an equal to n factorial divided by n to the n. So this is the first place when we encounter factorial in this course. We will deal with a lot more factorials when we start talking about power series. So this is a good occasion for us to investigate this function. So the question is, as before, compute the limit of this sequence, or determine whether it is convergent. If it is, compute the limit. Okay, so what we want to recall is what is n factorial? How is this function defined. So for a positive integer n factorial is the product of all positive integers starting from 1 all the way up to n itself. For example, 1 factorial is 1, 2 factorial is 1 times 2, 3 factorial is 1 times 2 times 3, and so on. So for any number, any positive integer number, factorial is the product of all positive integers up to this number itself. So we can continue this sequence. As you can see, an important property of factorial is that it grows to infinity quite fast. So now let's investigate the limit of our ans. So now that we have defined n factorial, let's look at this limit. Whenever you are dealing with factorials in the context of limits, you want to rewrite factorials as products. So I'm going to rewrite this expression for an as product of n terms in the numerator and product of another n terms in denominator. So in the numerator, I will have, according to the definition of factorial, I will have a product of n terms going from 1 to n. So here is the product in the numerator. In the denominator, we have n raised to the nth power. So what is a number raised to the nth power? Well, n is a positive integer. A number raised to the second power is the number multiplied by itself. A number raised to the third power is the number multiplied by itself 3 times, 2 times, depending on how we count it. So it's basically, in general, a number raised to the nth power is equal to n factors, each of them equal to this number, equal to the base of the power. So in this case, we have n factors, because the exponent is n, but the base is also n. So each of these n factors is equal to n itself. So this is the product that we are looking at, right? So it is important to notice that an is non-negative. On the one hand, an is non-negative because we're multiplying some positive numbers. Of course, you cannot get a negative number as a result. Secondly, what we want to do is we want to group these n factors like so. Okay? What can we say about these fractions? You can see that we can rewrite the limit as product of n fractions. 1 over n, 2 over n, 3 over n, and so on, up to n over n, aka 1. Right? So we have n fractions. What can we say about them? Well, the first fraction is quite small, right? So it goes to 0. How about the other ones? Well, all of these, they don't really go to 0 in general because n over n is always just 1, regardless of what n is. But one important thing about these is that they are all at most 1. Right? This is less than 1, this is less than 1, and so on. And the very last one is precisely 1. N over n is precisely 1. But in general, all except for the very first one, they are less than or equal to 1. So we start with a positive number, 1 over n. We multiply it by several numbers which are all at most 1. Right? So it means that this expression here is at most 1 over n. So we start with 1 over n, we multiply it by several terms which are at most 1 each. So the maximal value we can get is 1 over n. On the other hand, we just observed that a sub n is non-negative. On the other hand, we have 0. So this here is another suitable, example suitable for applying the squeeze theorem. On the left, we have a constant sequence, which just consists of 0. Obviously, its limit is also 0. On the right-hand side, we have non-constant sequence, which goes to 0 when n goes to infinity. So in the left-hand side, something that goes to 0, on the right-hand side, something that goes to 0. It follows that the middle part of this double inequality, which is, by the previous discussion, exactly an, the middle part must also go to 0. Okay? When n goes to infinity. And so it follows that the limit of this expression, which is an, is exactly 0. And so even though n factorial goes to infinity really fast, n raised to the nth power grows even faster, so that the ratio actually goes to 0. In the next example, we will talk about convergence of r raised to the n for different r's.